Welcome back to our course. So in the last session, we have seen that the Python standard library is quite limited when it comes to large numerical operations with lots of iterations and loops. It's simply too slow and requires too much resources. But before we move to the more efficient NumPy package to boost our performance, we still want to answer some more advanced questions with our code that we have right now. And therefore, we are now using only 10 simulations, and that do the job as well for our purposes here. But we should keep in mind that our results might be heavily influenced by random noise. So in the last session, we figured out that on average, we need to purchase 1,491 stickers in order to receive 550 unique stickers. And I have to admit actually that this was solved manually by trial and error, or at least it was kind of a very informed guess. But what we actually want is we want to have a smart algorithm that does the job for us. And therefore we now start with a quite simple algorithm. I call it naive or inefficient solution, but let's see what we get. All right, so we set our target to 550, so we want to have 550 unique stickers, and we set our purchase stickers randomly to 800. So our random starting point could be any number, could be 100 or 2000, but for now we are starting with 800. And let's execute the cell. Let us now calculate the result given purchase stickers equal random start. So we start with 800 purchase stickers and we set sims to 10 to be more efficient. And we will get 444.7. So our target is 550. We have 444. So we are a bit away from our target. And now we want to increase our purchase stickers to say our random start by one sticker as long as our result is smaller than our target, and therefore we are introducing a while loop. So while our result, here our starting result with our random start is 444, is smaller than the target is 550, please increase the amount of stickers I buy. So in the next loop we will have 801 stickers. And after that, please recalculate the result and print both. So that's actually a quite simple and easy algorithm, and we can start it. You can see, so our first simulation 801 results in 444, and it takes a bit. We know that in the end we end up with about 1,400, so it's still calculating. And now the algorithm ends, and we are, our result is actually that we reach the target with 1,430 purchase stickers. You might ask, oh, there's a difference. Before we had about 1,491 stickers, but keep in mind that we reduced our simulations here to 10, so the random noise is a bit larger than if we use 1,000 simulations. And in the end, then we can print the current or the actual random start, which is now the expected amount of purchase stickers that we need to receive 550 unique stickers. So in this case here it's 1,430. You are correct in saying that, okay, that's not really a smart solution, just increasing the amount of purchase stickers by one as long as we are below our target. So we now introduce a smarter solution, and we are using an algorithm which is heavily used also in machine learning and deep learning in solving neural networks. Of course, they are more complex in these applications, but the idea behind it is actually the same. So we are starting our algorithm with a random start, also 800, could be any number, and also our target didn't change, it's 550, and we are introducing a learning rate. And I will explain in a few minutes what a learning rate, what the function of the learning rate is. So let's execute, and first of all, we calculate the result with, we have an album capacity of 600, we have purchase stickers, we are putting in the random start 800, we have 10 simulations, okay, the seed is 1, 2, 3, and we end up with a mean of 444.7. And what we are now doing is actually we are calculating the delta or the difference between our result, 444, and our target. So it's minus 105. So minus means that our actual result is 105 unique stickers lower than our actual target. And what we are now doing, we are updating our random start. So our random start is equal to our random start before minus learning rate times delta. So learning rate is now 1, so we can just forget about learning rate. But we are changing our random start by the delta. We round it because there's no fraction of a random start or stickers we purchase, so we cannot make fractions of stickers. So now we are updating our random start, and we are ending up from 800 initially. We are now at 905. So why are we at 905? Because we had a delta of 105. So before our result was 105 lower than our target. And according to this formula here, learning rate is 1. We are increasing our random start by 105 by the delta. And given our new random start or the amount of stickers we want to purchase, we can now update our result. So if we buy 905 stickers, we end up on average with 468 unique stickers. And we can, of course, recalculate the delta. Now it's minus 81, and we can again update our random start. So now in the next iteration, we start with 987 purchase stickers. And we go back and recalculate it, and we can repeat this many times until we come very close to our target value of 550. All right, so that was the intuition behind our algorithm, and now let's automate our algorithm a little bit. So we have still random start 800, target 550, learning rate we keep at 1, and we introduce epochs. So what does epochs mean? So before you have seen that we can iterate here many times, and for example 100 times, and then wait to get very close to our target value. And with epochs we can set a maximum or a limit of iterations so that we keep efficient actually. So 1000 iterations might not be a good idea, and in the end we can have also the learning rate, which we will see later, that we can vary to reach our target. And therefore we can use a for loop with exactly 20 iterations. So in range epochs equal 20, and for each iteration, as we have seen here above, we are calculating the result, calculating the delta, and printing a random start and result, and adding a multiple of our delta to random start, and then we are starting again an iteration. So let's execute the cell. And here we are seeing, okay, we have 20 iterations, and we end up with the 20th iteration at a average value of 544 and purchase stickers of an amount of 1,413. So now we could say that 20 epochs, so with 20 epochs, we don't exactly match our target. We are five stickers away, and it could be a little bit faster how we adjust our algorithm, and there comes the learning rate into the game. And by increasing the learning rate, we increase the magnitude by what random start will be adjusted. So I would expect that here our adjustments will be a bit larger. So the first adjustment was an increase from 800 to 905. If we increase the learning rate, which will be multiplied with delta, then I would expect that our algorithm will be faster in the end, and we can just now check it. So we can see here, we are coming very close to 550. So after 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, after 14 iterations, we are only 0.2 pictures away from our target. And we can further increase the learning rate and hopefully getting even faster. So now we are reaching approximately 550 after only 4 iterations. So let's try 10. And there you can see our result is suddenly higher than the target. And this is adjusted then afterwards again. But learning rate of 10 might be too high actually. So when we try 100, we are getting nowhere. So this is the settings, the learning rate is kind of an art actually, or you have to be very careful and you have to try it out. And I think in our case, the best learning rate should be between 5 and 10. So let's take 7. All right. So with learning rate 7, we end up very close to 550 after only 5 iterations or 4 iterations. And our algorithm also works when we are starting from the opposite side. So if we are starting with a very high number, let's say 2000 purchase stickers. Let's see. Okay, and also from here we are reaching 550 after 5 or 6 iterations. So our algorithm with learning rate 7 should be quite powerful. If you start from a very low starting point or a very high starting point, it doesn't matter. So our algorithm can do both. All right, so that's it for this session. And in the next session, we are finishing our algorithm. We are just doing a bit of fine tuning. I hope you enjoyed it, and we see us in the next session. Bye.